I said yesterday that basically our techniques are one of two ideas, boils down to it, substitution or by parts. Let's look at substitution again, but let's look at the non-standard integrals. So these are not on the reference sheet, but certainly come up a bit. I've talked about this one before. So du on root u turns out to be 2 root u. It comes up a lot. Another one that comes up a lot is du on u squared. Well, that one would always be minus 1 on u. Log of x log x minus x. Tan, we've seen that one. Log of sec, or if you prefer, minus the log of cos. Now these three, they used to be on the reference sheet. For some reason they took them off, don't know why. They might be given to you in the question, they might say using that, or they might ask you to prove them, but if it's neither of those two, it's still okay to just quote them, they're standard integrals. So sec tan goes to sec. These last two are interesting, they're pretty much the same integral, but just notice the square root sign matches. So really it's 1 on the square root of x squared plus or minus, doesn't matter, a squared will be the log of x plus, always plus, the square root of whatever is in that surd. If you're looking at it, and now you have to choose, that's the big difference I guess with extension 2 and extension 1. We're going to have to work out a substitution for ourselves. Now what's causing the problem? And usually it's going to be the grouping symbol, whatever's in the grouping symbol. I've got x squared plus 4 in the grouping symbol. If I wanted to do it via substitution, we get u equals x squared plus 4, that's what's in the grouping symbol. There it is, look, in the grouping symbol. Du is 2x, and so we've got a half of that there, and so we know it's the same as going a half of u to the half, which is 2/3 u, 3 on 2. Substitute back in. Oh, let's make it look pretty. There we go. But again, if they're not giving you the substitution, a better way of doing it is recognising derivative times function. It's going to be quicker. Of course, another way you could do this, when you see square roots and then the sum or difference of two squares in there, maybe you can do it via a trig substitution, because you can turn what's under that square root sign into part of a trig identity and then turn the two terms into one term. So for this one, I might go, well, let's say x is 2 tan theta. That means dx is 2 sec squared theta d theta, and I can substitute in. So the x is 2 tan theta, the square root of x squared plus 4 becomes 4 tan squared plus 4, square root of it, and then dx 2 sec squared theta. Well, let's look at that square root. Tan squared plus 1 we know is sec squared, so 4 tan squared plus 4 must be 4 sec squared. The square root of that would be 2 sec. Multiplying it with the other 2 sec squared, we get 4 sec cubed, but then another 2 out here, we get 8 out the front of the whole thing. I now have tan theta sec cubed. Not sure how to handle it. I'll change everything into sines and coses. I end up with sine theta on cos to the power of 4. It is in the form of derivative on function. But if I didn't see that, I could do another substitution. So, well, let's u equal cos theta. Du is minus sine theta d theta. Substitute in for that, and eventually we get it down to a nice simple integration. Add 1 to the power over the power. So there it is in terms of u. Substitute back in. U was cos theta. I get sec cubed. Now I have to substitute back in to get the x's. Well, how on earth do I do that? We know x equals 2 tan theta. If I just draw myself up a little triangle, so x is 2 tan theta, opposite is x, adjacent is 2. We've got to work out the hypotenuse. It's not a coincidence that the third side of the triangle turns out to be that surd in the original question. Square root of x squared plus 4. But now I can read off that and say, well, what's the sec of theta? Well, that would be sec, reciprocal of cos, isn't it? So that would be hypotenuse over adjacent. Sub it in, we have our answer, same as we got before. Now, I'm not saying that's the most efficient way of doing it, but it is an alternative substitution you could use for that one. But as I say, always keep an eye out for that. If you spot that straight away, it's going to be the quickest way of doing it. Is it derivative times some function? What about about this one then? X times the square root of x plus 1. Temptation is to make u equal x plus 1. Well, it'll work, you'd get there. But what about if we made it the whole square root, the whole thing that's causing me the problem? That means x is u squared minus 1. Why did I make x a subject? Just to make it a little bit easier for the substitution, because I can substitute directly in for dx if I do it this way. I get dx equals 2u du. So substituting in, x is u squared minus 1. I can go straight in for that. We said the square root of x plus 1 is u, and dx is 2u du. I can now do a nice easy integration. Add 1 to the power over the power. Substitute back in. Mere mortal answer. Here we go. Another way I could have done that one. X times the square root of x plus 1. I could have done some algebraic manipulation out the front. I could have rewritten x as x plus 1 minus 1. Then broken that up into two integrals, and I get x plus 1 to the power of 3 on 2 minus x plus 1 to the half. Add 1 to the power over the power, and you can see we get the same answer. I don't know if you spot it straight away, but we do have derivative times some function. The derivative of the square root of x is 1 on 2 root x, and we've got 1 on root x, so it actually is there. But you don't spot it, you go, okay, what's causing me the problem? Probably the thing in the grouping symbol. So u is 1 plus root x, making, and there it is, the dx on 2 root x that I was looking for. This one, of course, we've got to be careful with our limits. Change those. Now we can do our substitution. Here we get 2 lots of the integral going from 2 to 3 of just the u on u squared. Just a word about the separation of variables here. So it is important to separate the variables before you substitute in. So never do that sort of substitution. Sub in for dx where it's in terms of two different variables. One was the original variable, one's the thing I'm substituting in. It just is messy and doesn't make sense. Your limits must always be with respect to what you're changing it to. You're making it with respect to u, so my integral should be completely with respect to u. Everything in there is respect to u. Alright, back to our integration. So substituting in, we end up with a third. There it is again. We do have derivative times function there. So again, if you spot it straight away, that's going to be the quickest. But okay, we didn't spot it. What's causing me the problem? Probably the thing in the grouping symbol, which technically is the sine x. It's to the power of 5. So u equals sine x to u is cos x. That's some limits I need to sort out. But now we can substitute straight in, and we've got a simple little polynomial. Well, very simple. It's only got one term. U to the power of 5. Add 1 to the power over the power. Substitute in. We have our answer. Bingo, there it is again. Look, derivative function. Bang, spot it straight away. Get it. All right, I don't see it. What's causing me the problem? That grouping symbol. I'll make u equal 25 minus x squared for this one. So the u will be minus 2x dx. Sort out my limits. Substitute in. Oh, there it is again. du on root u. That's 2 root u. So we end up with 1. I can't do this one as derivative times function. There's no way I can manipulate the coefficient of 1 and get it in terms of x squareds and x. Can't do it. Maybe I'll try a trig substitution. Let's turn it into a trig identity. If I make x equal 5 sine u, in other words, u is the inverse sine of x on 5. That's another way of thinking about it. But dx is 5 cos u du. Why did I bother with u equals the inverse sine of x on 5? Well, because I've got some limits to substitute into, and that's just going to make it a little bit easier for me to work out what those limits are. So when x equals 0, u equals 0, x equals 5, u is pi on 2. Now, square root of 25 minus 25 sine squared, well I know 1 minus sine squared is cos squared, so that must be 25 cos squared. Square root of that is 5 cos times by the other 5 cos, and we get 25 cos squared u. Cos squared, we know how to deal with that. We'll use our double angles. That's 1 plus cos 2u. I can now integrate, substitute in 25 pi on 4. But of course that's not the best way of doing that one, because hopefully when we see the square root of 25 minus x squared, we recognise what that is. It's our semicircle. We're going from 0 to 5, which means I've just got a quarter of that circle. Quarter pi r squared, 25 pi on 4. A lot quicker. The idea of integration by substitution, but as I say, the substitution is not necessarily given in extension 2. Sometimes they still give it to you, but most of the time they don't.